Okay, the purpose of this video is to demonstrate how to predict who is tied to whom, as in who gives advice to whom. So the way I'm going to do it, I'm going to use regression. It's a special kind of regression that is designed for networks, for whole matrices, and not the kind that we're normally used to where we are just using two vectors, two columns of data. So to do that, I can press Control R. It's kind of buried in the menu, so Control R is a lot easier to do. So I press Control R. As the dependent variable, I have a data set called Neogen, and I've got the Lexington site, and I'm going to use advice as the thing to be explained. That's what goes under dependent variable. The independent variable is what we're using to predict that. So I will see what my choices are, and here's the required one. So I throw that in, and again, required just means that you're required to interact with that person because of the way your jobs mesh with each other. So I press OK. It runs a regression. It says the R-square is 0.512. That's very high. That's predicting a great deal of the variance, and it's highly significant, which means that this high R-square didn't happen by chance. And when we say highly significant, we mean that the number is extremely small, smaller than 5%, which is the conventional cutoff. So we know that advice is, in part, a function of who do you need to interact with for work. What else might be a factor? I'm going to close this and take a look at what other variables we have on these people. And I know I have something called Lex ATTR attributes, and I've got gender, so that might be interesting. Status, I don't know what that is. Education could be a possibility. Oh, and tenure. Tenure, it seems like you're more likely to go to someone for advice if they've been there longer than you. So let's take a look at tenure. Now notice that tenure is an attribute of each person. What I need to do is convert this into something that has to do with the pair of people, because I'm going to predict a tie between them. And so really what I want to do is create something like who has more tenure than whom, or what is the difference in years between them. To do that, I can close this and go to Data, Attribute to Matrix, put in as my attribute data set, in my case it's Lex ATTR, and here my attributes appear, and I can put in tenure years, and I need to calculate some kind of relational metric that compares each person's tenure with everybody else's, and the obvious thing to do is to just compute the simple difference between them. The result of all this is going to be called, I'm going to shorten this name here, it's going to be called diff 10 years, which is ugly but serviceable. So let me press OK. And now it gives me this matrix where we've got people as the rows, people as the columns, and this 5 right here means that person 9 has been in the company 5 years longer than person 10. And by the same token, person 10 has been at the company 5 years less than person 9. So I'm going to throw this in as another predictor of who goes to whom for advice. And I'm expecting the relationship to be negative, right? Because if I go to people who are older than me, that is, they've been there longer, that means a smaller number here. So person 9 has been there 5 years longer than person 10, so I expect that person 9 will not go to person 10 for advice. In contrast, person 10 has been there 5 years less than person 9, so I expect that person 10 will go to person 9 for advice. So the -5 should be associated with going to advice, and the +5 with not going to advice. So I'm going to press Control R, and I'm going to add in now this new network that we created, difference tenure years. and run it. Okay, the R-square has not really changed much. So we haven't done a great deal in terms of improving our fit. It is significant, but it explains almost nothing here. This is almost zero, the standardized coefficient. It is negative, which is the direction that I expected. So there's a slight tendency for people who have been there less time to go to people who have been there more time for advice. All right, what else could we add? Well, I noticed that there was gender in there. I wonder if people tend to go to people of the same gender for advice. So let me go to Data, Attribute to Matrix, and change the attribute to gender. And here I'm not going to use difference in gender. I'm going to use exact matches, which just means it's going to be a 1 if the two people are the same gender and a 0 if they're different genders. And I'm going to call the result of this same gender. So I'll press OK. And so there's a 1 here between person 9 and person 21 because they are the same gender. It might be both female or both male. And there's a 0 here because these two are different gender. So I close this, I press Control R, and now I add in same gender. If only it would show up. Where is my same gender variable? This machine is like that sometimes. Well, I bet it's there. It's just not sorting yet. Same gender, yep. It was there. Okay. And again, the R-square is not really doing anything, and same gender was not significant because that p-value is greater than 0.05. In other words, what that p-value says is that there's really like a 30% chance of getting this strong a gender effect by chance alone, which means it could well have happened by chance. And you can see that this is basically 0 here. So it looks like the one thing that we've been able to figure out so far that determines who goes to whom for advice is whether their jobs are interlinked. And that's it for this video.